Okay, we're starting a new chapter. This chapter is going until probably up until we review for the final exam. This is the last sort of main component of this class. So remember the very first day I told you this is a class about logic and proofs. It's a class about counting, and it's a class about graphs. It's graphs. We've made it. And so homework 9 is going to be some remnant of chapter 11. So that should be fairly straightforward. Then homework 10 and 11 will be on these topics. All right. We're going to talk about a lot of definitions today. And so it's a lot of writing, a lot of things are moving quickly. We're talking about new terms. I've made a document that is, so I imported it into this document. It's basically just, here's all the definitions that we're talking about today. This link, I've given you a read-only link, and that link can be found on Canvas. Graph definition cheat sheet, view only. And so we click there. Open link in new tab. Voila. So you can access this, refer to that. We're going to go through each of these definitions today and talk about what they mean. All right. I'm going to do my very brief pitch on why you should care about graphs. Graphs are all about relations between things. So we can say, I have a fish and another fish, and these fish do not like each other. This is my attempt to draw angry fish. These fish don't like each other. We can abstract this relationship of these fish, like one of these fish will eat the other. We can abstract that into some general structure. And that structure is a graph. So the kind of graphs that we're talking about is not your parabola of XY axes, although it is related. So your XY axes, if we have something like y equals x squared, or f of x is equal to x squared, that is actually some pair of data where if you give it x of 0, you get a y of 0. If you give it x as 2, you get y as 4, right? So even your normal XY graph is consisting of pairs. We're also going to consider pairs, except they're going to be way simpler because on an on a real number axis, you've got not only 0, 1, 2, the integers, but you've got 1/2, 1/3, square root of 2. And so we don't want to deal with all of those. And so we're going to consider a discrete set of objects. So not the whole real number line, but since this is discrete math, we'll consider like individual things. Like this is a fish. That is a fish. They're two separate objects. And so graphs are all about relations. And so this relation can mean anything. It could mean these two fish hate each other. It could mean if we've got the people in this class and some people are friends, but other people are not friends, we can draw a line between these people to say they are friends. Hatred or friendship, right? This relation can mean whatever we want it to. The objects in question can be whatever we want it to. It could be, so we're working with a project over summer, and we said that the objects are going to be triangles and the edges between them. So we say that these two triangles are related if they appear next to each other. The objects can be what we want them to. The relations can be what we want them to. All we have to do is define it properly. Okay, so let's talk about our definitions. I'm going to scroll past that and maybe come back to it. So we are talking about graphs. A graph is a pair of collections. Two collections, one of which is the objects, which we call the vertices. The singular of vertices is vertex. So, for example, my fish is an object. That is a vertex. If I have two fish, I've got two vertices, but this fish is a vertex, that fish is a vertex. So these are just the objects in question. The other part of that pair is the edges, which is when that's the relation to say these two fish hate each other, so we're going to draw a line between them. This is the relation between two vertices. We are limited, so okay. We call the vertex set capital V. We call the edge set capital E. And so we write a graph as G, capital G, is equal to the ordered pair in parentheses, V comma E. And so this is standard. And so we know that the first thing in that set is the vertices. The second in that pair is the edges. Okay, let's look at an example. So we have G equals V comma E, where V is equal to the set of A, B, C, D, and E. And E is equal to the set of A, B, B, D. I'm leaving space so I can write something later. B, E, and D, E.
Is there an issue if V contains a capital E too, or we just, oh, is that an F?
No, it is neat. So not really. It kind of depends on, again, like terminology and notation are pretty much what you make of it. So if you're super clear that like that's not the same thing as your edge set, then that's fine. If we wanted to remove confusion, we could make it F instead of E. Just to be sure. And so our edge set is this list of pairs to say these two vertices are next to each other. These two fish hate each other. And so the book writes them with curly brackets, which is okay. I typically write them with parentheses for reasons that may become clear later, because sometimes the order here matters. In this case, they don't. Where you'll notice in the fish problem, here, let me scroll quickly back up. So A is enemies with B. B is also enemies with A. So this relationship goes both ways. So A doesn't like B. B also doesn't like A. Sometimes it doesn't go both ways, but that would have to be specified. So for now, we just assume that this relationship goes both ways. And that, I think, is why the book uses the curly brackets to say this. Okay, so that's nice that we have a list of things. I don't know what it means. So now we get to draw a picture. Graph theory is kind of like we're I love this class so much, just in general, because it's like we're going back to kindergarten of like, how do you write something? How do you count? And we're connecting the dots. So we're going to draw each vertex as a dot. So we're going to say this is A, this is B, this is C, this is D, and this is what I have renamed to be F. Okay. And now I can go through my edge list and say, and draw the line, connect the dots. So we have an edge of AB, so A connects to B. We have an edge of BD, B connects to D. We have an edge of BF, so we connect those dots. And then finally, we have an edge between D and F. And that's it. Once we do that, there are no more edges. And so this is our graph. All right, an assumption that we're making here is that when we write an edge, we require both things that define the edge to be distinct. So when we write D and F, we could not choose to write D and D. What that would do is that would make what we call a loop, which we tend to ignore. There's also something called a multi-edge, which is where if we draw, there's already an edge between F and D, but if we drew another one, that is what we call a multi-edge, because now we've covered that edge twice. And so generally we ignore such cases. So we assume that if we have an edge, let's just call one of the things U, the other thing's V, U cannot equal V. And if we have an edge in our edge set already, we can't have it again, right? So there's no duplicates. Okay, so no duplicates allowed. So if we don't allow loops and we don't allow multi-edges, we say the graph is simple. If the graph has loops or has multi-edges, we say it is not simple, or we call it a multi-graph. Most textbooks mention this at the very beginning and then say, we're not going to worry about multi-graphs. So I'm doing my duty. We're not going to worry about multi-graphs. We're assuming the graphs are simple. So no loops, no multiple edges. It's not that it's complicated, it's just reduces redundancy. So we are going forward assuming that we're working with simple graphs. Okay. So the next definition is, let's say we have two vertices, U and V are both in our vertex set of G. Sometimes we say V parentheses G to say that we're looking at the vertex set of G. Sometimes we just say V because if we're only working with one graph, what other graph would we be talking about? So it kind of depends. But let's say we've got two vertices in this graph, and we say that they are adjacent if they're joined by an edge. So that means that now that we also have talked about logic and we know all of these set theory notations, we use them a lot. And so we can say that the edge UV, which we denote as this ordered pair with parentheses, is in the set E, or similarly E of G. And that parentheses just says, here's what graph we're looking at. Okay, so they're adjacent if there is an edge. Anyone want to harbor a guess for what not adjacent means? They're not joined by an edge. Again, like, it's really like fairly straightforward where like if two things are next to each other, then we say they're like adjacent to each other. And so we just define next to each other as they're joined by an edge. Question.
If you were to write notation for that, would you write not E, like in not E, or?
Yeah, so would be U and V are not in my edge set. So you just draw a slash through it. Okay. So let's go back up here. I'm going to, okay, let's pretend, I'm going to leave the purple in here for the notes, but let's pretend that they're not part of the graph. So are A and B adjacent? Yes. Are A and D adjacent? No. Is F and B adjacent? Is F and A adjacent? Right, great, you got it. Okay. The other term that the book brings up is isolated, which is just, it's a lonely vertex that doesn't have any edges. A vertex with no edges. Let me scroll up and ask you, do we have any isolated vertices here? Yes, which one? C. C's lonely all the way over here, no edges. Okay. We say that a vertex has some degree, which is, so the degree, let's say, of a vertex, let's call it V, lowercase v, is the number of edges that V has. We denote this as lowercase deg, parentheses, and then in the parentheses goes the vertex we're talking about. So deg for degree, and then which one are we looking at? All right, let's go back up. What's the degree of B? 3. What's the degree of D, assuming that the purple stuff doesn't exist? 2. What's the degree of D, assuming the purple stuff does exist? 1, 2, I think it's 5. So that would be 1, 2, 3, 4, 5. What's the degree of F, assuming the purple stuff does not exist? 2. Great, you got it. All right, that's degree. And so like the degree, we write it degree of the vertex in question is equal to 2. Sometimes if we want, this is a question on the homework. Hold on, I'll do that in just a second. Sometimes we want to write what's the degree sequence of the graph. So like what are all of the degrees of all of the vertices? And so let me actually do it back up here. And so the degree, I'll write it in pink, of A is 1, B is 3, D is 2, F is also 2. And so we write the degree sequence in increasing order. And so the degree sequence would be 1, 2, 2, 3. Okay, question?
We were counting as a multi-graph, shouldn't the loop only count as one line? Cause it's,
Right, so
One line.
yeah, so it is one line, it is an edge, but because it leaves D and comes back to D, it counts as 2 for the degree.
For the degree sequence, do you not include 0, like for C, and help?
You would include C.
Oh.
Thank you. Yeah, the degree of C is 0 because it has no edges. Yes. Okay. Okay. So we also can talk about neighbors. Sometimes graphs are very friendly because we can say that something has a neighbor. So a neighbor is the neighbor of a vertex is all of the vertices that vertex is adjacent to. So if I have U and it is adjacent to W, X, and Y, and there's also some Z that W is not adjacent to, then that's not correct. Well, it's adjacent vertices. The neighbors of U, which we can denote with a capital N, and again, in parentheses, we say which vertex we're talking about. And this is a set of the vertices it's adjacent to, which in this case is W, X, and Y. What are the neighbors of Y in this graph? UX is not correct. U and Z. So Y has an edge to U and also an edge to Z. U and Z. So that's the set of all the neighbors. This is also called a neighborhood because that's all of them. And so we can say that W is a neighbor of U, but the neighborhood of U is W, X, and Y. Okay, we've got this topic of regular, where we've said degree is the number of edges that a vertex has. A graph is regular if the degree is the same for all of the vertices. So G is regular if the degree the same for all vertices. So let's look at a regular graph. So if we look at each vertex in this graph, this top one has 1, 2, 3, 4. The bottom right has 1, 2, 3, 4. The bottom left, 1, 2, 3, 4. And then this upper left in the middle, 1, 2, 3, 2, 3, 4. And same, 1, 2, 3, 4. 1, 2, 3, 4. The degree for all of these vertices is the same. And so this graph is regular. In this case, it's often helpful to specify what kind of regular. And so we say the number of the degree, which is the same for all of the graphs, which is 4 in this case. This is actually an interesting concept for me personally, because the graphs that I look at tend to be 3 regular, because I look at like triangles, which are adjacent to each other. Each triangle has 3 sides. And so if I convert each triangle to a vertex and then set the edges as these 2 triangles live next to each other, then my whole graph is going to have degree 3. Okay. All right, so let's redraw our original graph for a moment. A, B, D, C is over here. We've called that F. So I would like to consider so like maybe I don't want to look at the entire graph. Maybe I want to look at this a subset of the graph. So I'm going to call this a subgraph. And this means I've got the freedom to pick and choose what I want to be included. So this means I could choose, for example, I could choose A, B, that's called F, that's D. So like this is a subgraph of my original graph. So if I call this graph G, and then I can give this another name. So usually it uses the same letter as the original graph. Sometimes if we're working it with 2 completely separate graphs, we'll call them like G and H. We started G because G stands for graph. But again, these are just, it's set theory. So the letters that we choose don't really matter. This is just convention for the most part. And so when we're naming a subgraph, sometimes we use G prime to say it's like G, but just a little bit different. And so then if you have different subgraphs, you can add on however many primes you want. Sometimes we also give them numbers as a subscript. You could give them numbers as a superscript, but I think that it tends to mean something else. So proceed at your own risk. Typically calling it like G prime or G sub 0, G naught, that's pretty standard. And so we can say that that is G naught. We could say that if we've got C over here and D over here, this could be G1. Right, so we've got freedom to choose which vertices, which edges to include. So let's see. So the definition is a subgraph. Maybe it helps if I spell graph correctly. So how do you spell graph? PH. I've been working with graphs how many years?
I thought it was GRF.
Oh, yeah. So a subgraph of G equals V comma E is any graph, I'll denote it G naught here. And so similarly, to avoid confusion about our original sets, our original groups of vertices and edges, we need to say that like these are the vertices I'm including in this set. These are the edges that I'm including. And then we have the restriction where the vertex set that we've chosen has to be a subset of our original vertex set. And similarly for edges, it's just got to be a subset of the original. Provided that, let's see, the term that the book says, every edge selected for E naught has its endpoints likewise selected for V naught. So how do I want to write this? So provided that the edges selected in E naught have their vertices in V naught. So that just means that like if I chose the edge AB, A has to be in my list of my subset of vertices. B also has to be in my subset of vertices. I can't choose the edge AB and not include one of A, like either of A and B. Okay. The complement of a graph is so if we have a graph G, the complement is written G with a line over it. And so let's consider something relatively simple. Let's consider this to be my G. And the complement is basically anything that is in my graph currently is not going to be there. Every edge that's in there won't be there. Every edge that's not currently there will be there. So it's just like we've completely flipped it. It's inversed. So I still have the same vertices. I still have A, B, and C. But now, so there was an edge between A and B. It's not going to be there. There was an edge. There was no edge between A and C. So it's going to be there now. And there was an edge between B and C. So that's not going to be there. Right? So we've just completely inversed the graph. This is the complement. Okay. Let's talk about a complete graph. A complete graph, and this is, so the next few definitions are, we have an assumption that we're talking about a complete graph on n vertices. And a complete graph is just, so let's say we've got 3 vertices. A complete graph is just every possible edge is included. So we've got 3 vertices. So every possible edge means that one, and that one. A complete graph. And so we denote this with a capital K for complete, and then sub n for the number of vertices. And so this is K sub 3. The other thing is the guys who came up with graph theory tended to be around Germany. And so a lot of the notation is also retained from there. And so let's look at K4 So not only we've got all those, and then all those, and then that. So now in a complete graph, every vertex is adjacent to every other vertex. So there's a nice formula for the number of edges in a complete graph. I will tell you that it's n times n minus 1 over 2. We'll probably look at this more in detail later. A null graph, which you hardly ever see, is just a graph with no edges. It's extremely boring. This is the null graph with 4 vertices. This is the null graph with 3 vertices. It's terribly boring. We never really talk about it. There's nothing interesting going on over here. A path graph, which we denote P sub n, so a path graph on n vertices, is so like if you think of a path as you're going from one, like I'm going to take the path from here to the statue. I'm going to walk in a straight line through Galileo, exit the door, end up at the statue. That's the idea of a path, which we see. It looks something like this. It's just a line of vertices. And I hope you can see that there are n minus 1 edges here. So this is P sub 1, 2, 3, 4, 5. And there are 1, 2, 3, 4 edges linking these 5 vertices. That's a path. There's also the notion of a simple path, which we'll talk about next time. There's a cycle, which is when we've taken our path and joined that first and last vertex. So we bring it around. The book calls it a circuit, which I do not like, but I suppose works. And so we denote that as capital C sub n. So for example, this is C4. This is C6. So the cycle on, wait, no, that's not C6. 1, 2, 3, 4, 5. I can count. Cycle on 5 vertices. Okay. With me so far? Cool. It's a lot, like, it's a ton of terminology. I'm aware. We need this terminology to be able to go forward. So what I would recommend is going home and looking at the document that I've made, make flashcards for it and drill yourself on it. That's the way that we're going to get through this. It's just a lot of terminology, but once you start to understand it, it's fairly straightforward. Okay. Let's talk about connectivity. So let's consider a triangle. Do you think all these vertices are connected to each other? I would say so. What about the path? Do we think all these vertices are connected to each other? Yeah, it's not a complete graph, but there's still a way to get from any vertex to any other vertex. And that's our definition of connected. So if there is a path between any two vertices, then the graph is connected. Great. Pop quiz. Okay, those are all three separate graphs. Is this graph connected? Yes. What about now? No, because there's no way to get from this guy to that guy. What about now? Yes. So if there's a way to get between every pair of vertices, there's no that are disconnected, then the graph is connected. And so if there is no path, then the graph is disconnected. We say that there's a notion of components, which is just how many things in one piece are there. So if we assume our graph is that one we had earlier, how many components does this have? Three. Right. There's one component. That's one component. That's another. Sometimes we call these connected components, which just says that each of the components is itself connected. The book says maximally connected, which basically, like, if every, yeah, I don't like maximally connected. What did I say in my notes? That's maximally connected. If the entire graph is in one piece, it is said to be maximally connected. Great. Sounds fine. Wouldn't worry about that one too much. All right, so a cut edge is, as its name implies, an edge where if we cut it from the graph becomes disconnected. Where its removal disconnects the graph. There is a cut edge in this component. Right, so it's this one. Where if we remove it, then A is off by itself. So that edge between A and B is a cut edge. All right, we're making good progress. So at the beginning, I drew a graph of A, B, D, C's over here, F's over here. This is a graph with labels. I think the graphs that you drew also have labels. We can draw a graph without labels by just not writing any letters next to them. Again, most of these definitions are fairly straightforward.
And how would you indicate something? Like if you were to indicate a vertex in a non-labeled graph?
Right, so it depends on what you're trying to model. So remember when, like, we saw this in combinatorics, where like, if the things are distinguishable, then we'll put labels on them. If the things are not distinguishable, then we won't put labels on them.
Then how would you be able to graph them as they're still distinguishable based off the number?
Right, so like, they are distinguishable in a way, but maybe they don't represent any particular thing that we're caring about. Yeah, so it kind of depends. How many ways can we assign labels to a graph with n vertices? N ways? I disagree. Also not n squared. How many ways can you assign labels to a graph of n vertices? Yeah,
Is it n times?
it's not n by itself, yeah? N factorial. Because we can assign them one for, you have n options to start with. Once you assign one, and then it's a sequence of decisions. Then you've got n minus 1 things left. And then you've got n minus 2 things left. And so on. Okay. Isomorphic. This is, so we talk about isomorphism after we talk about labels. Isomorphic basically means it's got the same structure. So even if we label all of this differently and we move the vertices around, the other thing about graphs is like the placement of the vertices does not matter. We could draw it like this, we could draw it like that. It's the same graph. Well, assuming that we have that C over there. It's the same graph. We can move them around, doesn't matter. If we assigned different labels to these graphs, that would be fine as long as we can identify a correlation of like this vertex matches to that. So if I chose W, X, Y, Z, and V, then I can say that A corresponds with W, B corresponds with X, and so on. That's isomorphism, where they're, okay, I don't know what iso means. Morphic means like, I don't know, moving. And so it's the same when you move things around. It's the same structure. Okay, we're hurtling towards the end. I've got 2-3 things left to talk about. One of which is how do we store this information? So like if you go to code a graph, how do we represent it in code? One of which the options is an adjacency matrix, where if I have a graph of, let's say, A, B, C, and D, then I write those both as my rows and as my columns. And if there is an edge between 2 vertices, I put a 1 in that row and column. This also assumes that because we're dealing with simple graphs, there's a 0 in row A, column A, row B, column B, since there's no edge between a vertex and itself. So row C, column C, row D, column D, those are all zeros. There is an edge between A and B. So these are symmetric. There is an edge between B and D. There is an edge between D and C. So C and D. And there is an edge between, wait, D and C, D and C. Then there is an edge between C and A. So those spots get 1, everything else gets 0. Because there's no edge there. Something that the book doesn't tell you is there's also something known as an adjacency list, which is where either we have like a dictionary or a linked list to say that A is adjacent to all of these things, which is B and C. No, come back. B is adjacent to A and D. C is adjacent to also A and D is adjacent to B and C. So similar ways where all of the edges are represented, it's just a different format. All right, I think we have sped through all of those things. There is some additional definitions about bipartite, which we will probably look at the beginning of next time. Go home, make flashcards for these. Just go over them and just try and be a little bit more familiar when we talk about them in class on Friday. Thank you very much. Please bring your markers up to the front. Take some candy before you go. I will see you on Friday.